Alright, obesity and VO2 peak. Let's have a go. So it's in the sort of format as the previous weeks. Why study obesity? Why is it important? Why is it worth our time and effort? Then we're going to move on to thinking about how it might influence like one of these major variables of interest, VO2 peak. And then there's a bit of a spanner that gets put in the works. So it's not quite as simple as these other populations where we just go VO2 peak is lower, everybody's happy that it's lower, and therefore we can maybe start to think about some of the reasons of why it's lower in those individuals. There's an issue to do with how we kind of interpret the information about whether people have a lower VO2 peak or not. So issues of how we scale, which we're going to get into. And we're going to talk about that a lot because that's probably the most important thing within this literature. Towards the end, we're going to talk briefly about maybe the role of associated diseases of obesity and how they might be the really important factor that actually cause differences in cardiorespiratory function or VO2 peak. And then the kind of stuff that we've done in the past couple of weeks where we were thinking about these 5 methods of transporting oxygen, so the ventilation, diffusion, perfusion, diffusion, utilisation. Well, that's going to be more in your further reading because what you're going to see is that until you've decided what you're going to do above that with regards to scaling, it can have a massive impact on how you would actually look at any reasons why there might be any decreases or not. So, what is obesity? So we should all be pretty happy with obesity because we have talked about it in the past. To some extent we talked about it in the student health lecture because one of the outcomes we looked at. But obesity can have several definitions I suppose, but the most classic way of defining it is related to your BMI. So a healthy BMI sits between about 18.5 and 25. Okay, and we also talked about it because you all don't know anybody who's obese, right? And I do, don't I? We had that sort of session early on where it's like, how many people know more than 5 people who are obese? And none of you know anyone that's overweight or obese. I know plenty. But anyway, so to 25. So I think my BMI probably sits at about 23-ish, something like that. So I'm probably on the highest end of what someone would be considered normal weight. So just sort of maybe factor that in a little bit. Overweight between 25 and 30, and then we start getting into these different levels of obesity from 30 onwards. So sometimes they just get crammed together and say obesity is above a BMI of 30, and then often they get separated because considered like greater levels of obesity. I think there's even an obesity 4 now as well, which is greater than that. And that's important as well. It's something we're not going to talk about too much, but there's an interesting question of if you've got a BMI of 32, you're classified as being obese, and therefore it might influence other diseases, it might influence your VO2 peak, whatever. But are you the same as someone who's 52? Or is that a different population? Should we expect different results? So really thinking about how these weights people are classified might be quite important for your interpretation, especially when you're reading the literature. Not all obesity is likely to be the same. So why are we studying it? Why is it important? Well, again, we have talked about this in the past, but 2/3 of adults are overweight or obese. You don't know any of them, I do, but 2/3 of adults are overweight or obese. So this is like an epidemic, isn't it? It's all around us, it's everywhere. So you want a reason to study something. Well, it's a health-related issue that affects the majority of the population. It's huge. And possibly even sadder, it affects a quarter of 2 to 10-year-olds. So a quarter of kids are obese, are overweight. So it's a huge issue, and it seems like it's going up. Now, I'm not quite sure this will happen or not, personally, but I've got no reason to believe that other than there's some slowing of the charts looking at obesity. But the suggestion is that by 2034, 70% of people will be overweight or obese. So the number seems like it's climbing. Like I said, I've seen a few bits of data from this country at least, which sort of looks like it's plateauing off a little bit, but we'll see, I suppose. And then, so they're the kind of costs in terms of like it affects a lot of people. We know what it is, it affects a lot of people. And then again, if you want to, you can start talking about the kind of economic issue. You know, if you're trying to make a more global idea about why we should tackle it, well, clearly, if you're getting medication for being overweight, if you're having surgery for being overweight, if you're taking up doctor's time, if you're getting additional health problems that all need to be looked after, heart disease, lung disease, whatever else it might be, sorry, not heart disease, but lung disease, diabetes, things like that, it's going to have a huge impact from that, an economic standpoint as well. Now, what about health? Because this is what we really care about. So if you're ever making the economic argument, to me, make the economic argument after you've made the health argument. right? So some people wouldn't say that, but to me, we should be doing this to try and improve people's health, and then the knock-on benefit is that it might be better for the economy. I hate seeing it the other way around because I just don't think it's the right way. Right, so this is kind of just showing you, and there's loads of different studies all showing very, very similar types of information. And this is a meta-analysis, as you can see, 228 studies. So a massive, massive meta-analysis, so a study of studies. And within these 228 studies, it looked at over 30 million people, which included almost 4 million deaths. So we're talking a big piece of analysis. And all it's doing is it's looking at individuals' BMI, here along the X, and then on the Y is relative risk. So relative risk is the risk of something happening in comparison to a control. So what they've done is they've taken the lowest rate of death, being about, say, people with a BMI of about 23, so they're a 1, and then everything's in comparison to that. So if you've got, if you see a group that's a relative risk of 2, they have twice the chance of being dead in comparison to people with a BMI, say, of about 23. So that's how you should read into relative risk. You're relatively twice as likely to be dead. So what we can see is this kind of common-ish pattern. There's some argument about the exact shape and things like that, but this is the kind of the real take-home is that the ideal weight in terms of your overall mortality, so this is looking at people 20 to 25 years follow-up. So what is your weight now? How likely are you to be dead in 20 to 25 years' time? Okay, so baseline is here, 23, something like that, 24, and then we can actually look and say, well, actually, if you have low BMI, so you're underweight, there's an increased risk of death. So if you're underweight to about 15, say it's getting up to about 2. This is interesting. It's kind of not for today, but interesting questions about whether it's the fat mass itself that might be beneficial, that you need some fat, or it might be that these people are malnourished, which is why they have low weight, as opposed to being like healthy, fit, and have low body mass. Again, this sort of study wouldn't differentiate between those two things, but kind of an interesting thing there. But then the thing that we're really interested in is, well, what happens as BMI goes up so people become more overweight and obese? I know what you can see is almost this, at a certain point, there's a linear relationship between an increase in BMI and an increase in relative risk of death. So you can see at its highest at 45, so people with a BMI of 45, amongst these 30 million people, they were 3 times more likely to be dead after 20 to 25 years in comparison to people at a healthy weight. So we know what it is, and we know why it's important, and we know that it's affecting loads and loads of people. So it's not like there's very small numbers of people that have a BMI between 30 and 40, like it's 1 in 500. It's not, the prevalence is actually quite high, so it's affecting lots of people, and it's having huge health impacts. And so our next question, as it has been for the previous sessions, is, well, what effect does that have on VO2 peak? So our marker of cardiorespiratory fitness. Right, so to start thinking about this, I'm going to try and hand it over to you and get you kind of considering what you already know about VO2 peak and scaling. So, I've got 2 scenarios here. We've got a relatively small person, normal weight, who's got a height 1.6 meters. Their weight is 50 kilograms, which might make them underweight, but I'm just using these numbers to try and keep them simple. So if you kind of see it and you think, well, that's someone who's underweight, don't worry about it too much. I'm saying, smallest person, normal weight, their resting VO2 is 0.2 litres per minute, their VO2 peak is 2 litres per minute, so reasonable. And then if we scale that into making it relative to body mass, so millilitres per kilogram for body mass, they have a VO2 peak of 40 mils per kilogram per minute. Completely reasonable, all kind of healthy, normal. Now we've got another healthy person, normal weight, but they're bigger. So this person has a height 1.8 meters. Their weight is 75 kilograms, completely normal. Their resting VO2 is a little bit higher. Their VO2 peak is 3 liters per minute, and their VO2 peak represents their body mass is 40 mils per kilogram per minute. So my question to you, and speak amongst yourselves for a couple of minutes, is who has the greatest cardiovascular capacity between these 2 people? Right, so look at the numbers, try and consider it, see what you think. Have 2 minutes, speak amongst yourselves. Who has the greatest cardiovascular capacity or fitness? Okay. So if we got, what do we reckon? So who thinks this three options. Who thinks a small person's got a higher cardiovascular fitness? Hands up. Who reckons? Who thinks the small? Who thinks the big person? No? Who thinks they're the same? Oh, you saved me. I thought you were going to be up for anything. Right, okay. So everybody kind of, or a lot of you think the same. Okay. And presumably, that's because you sort of say, well, once we make it relative to someone's body mass, they've got the same number. Okay, so let's change it slightly, because I think you might be right, but it's well worth considering. If, let's say, this is a really weird thing to try and explain, but let's say you needed, well, let's just think about the heart. Let's say you needed a heart transplant, and you had the option of getting one of these people's hearts. Which one would you take? Which one, sorry? The one on the left. So this one, your left. Yeah, why?
So I was going to be a bit more efficiently than the one on the right, for their size.
But have we not accounted for that when we've done this value here? Because we've accounted for their size because we've made this number relative to their body mass, haven't we? So we've not accounted for that, and that's why these are the same. Would anybody take this person? Yeah, I think I probably would. Because my way of thinking is like in terms of cardio, like in terms of if they were going to run a race, you might think, well, they've got the same VO2 peak, and therefore this person's got relatively the same amount of capacity to be able to move that 50 kilograms of body mass, the same as this person has to move their 75. But if you just want to separate that and say, well, actually, if we look at their cardiovascular capacity, then maybe this one's cardiovascular capacity is greater. They can use more oxygen. Yeah, it's being dispersed over a bigger body mass, but maybe this is an important element in itself. Again, I'm not telling you it is or it isn't, I just want you to think about these things because this is really relevant when it comes to obesity. So, does anybody know why? You kind of forget that slide skip to, but why we make it relative to somebody's body mass? So, why do we do that calculation rather than just presenting it in absolute values? What's the purpose? What are we trying to account for? So, you're absolutely right, that's exactly what we're trying to do. We're trying to say people are different sizes, we're going to try and account for that in some way. But what is it about somebody that's 75 kilograms that's likely to make them have a higher cardiovascular capacity than someone who's not? When we think about cardiovascular capacity, cardiorespiratory function, we often think about the heart and the lungs, which is absolutely really important. But what's also important is the muscle mass that you've got as well. Because it needs something to be able to use that oxygen, you need that mitochondria. Right? So, you can kind of think about it, it's difficult because I know nothing about cars, so I'm far more out of my comfort zone talking about this than this. But for some of you, it kind of might make a bit more sense to think about a car rather than to separate it from what we already know. And so, again, I know nothing about how a car works, but I know it's got an engine. And so, the engine is the bit where all the kind of chemical reactions happen, right, where the energy is produced. Right? So, the engine is probably a little bit similar to the muscle, because that's where all the chemical reactions are occurring. So when a car's going, if you've got a car with a really big engine, like a big V8 engine or something like that, we know it's got a high capacity to use energy. And the rest of the car, so all the kind of cooling systems, the exhaust, and all these different things have to be of a size to match the size of that engine. Otherwise the engine won't be able to work, right? So that's what these things here, this is like air going into the engine and the exhaust pumping out the fumes. That's kind of what our respiratory and cardiovascular system is doing. It's taking air, it's delivering it to the engine, the muscles, and then it's getting rid of the exhaust, the CO2, back out again. Right? So these have got to match the size of that engine in order for it to be able to function. But we can imagine, if this is bigger, then that would necessitate that the rest of it needs to be bigger in order for it to function. Now, so if we've got a person that has a bigger muscle mass, then their potential to be able to use oxygen is probably greater. So then the only question then is the rest of the system built well enough in order to be able to utilise it or not? So that's kind of the reason why we try and normalise. We're sort of normalising for muscle mass as much as anything else. Right? Right. So, next question. Same scenario, slightly different numbers. Let's go through it. Same person, healthy person, 1.6 metres, 50 kilograms, resting VO2 0.2 litres, VO2 peak 2 litres, and VO2 peak relative to body mass of 40 mils per kilogram per minute. Now we've got somebody who's overweight or obese, well, obese in this scenario, 160 centimetres, 100 kilograms, same resting VO2 peak. They've now got a VO2 peak of 4 litres per minute and a VO2 peak relative to body mass of 40 mils per kilogram per minute. 2 minutes. Who has the greatest cardiovascular fitness? Okay, so let's do the same again. Let's get a sort of a, see if we've got a general consensus. So, who thinks this person's fitter, got greater cardiovascular fitness? Hands up. Okay, a few. Yeah, good number. Okay. Who thinks this one? The obese one? A few. Who thinks both the same? All right. So more split. So I'll probably still say more. Still saying the same. The least was that this person was the fittest, and then there's a few people saying the obese individual. So I don't know. There's no right or wrong to this. By the way, we're going to talk about some literature in a minute. It's going to put you in a certain direction. But whatever you think, I think you can make a case for it. So I suppose the reason I put this up to get you thinking about it is, well, if we make it relative to body mass, obviously their VO2 peak, so this traditional marker, if you like, would suggest that they have the same level of fitness. But this person's got twice the capacity, like if we look at it in absolute values, twice the capacity to take in, deliver and utilise oxygen. Twice as high. So this person with a VO2 peak of 4 litres is higher than most of the people in this room. Because we've measured a lot of you. I think one person might have got towards 4 litres out of a lot of you who did peak testing. So this is really high. So you put that number in someone that's 70 kilograms normal weight, and they're a good, distance athlete, really good. Whereas this person here, they've got the benefit of not being very heavy, and they've still only got, 40 mils per kilogram per minute. They're not getting any better. That's as good as it's going to get for them. So, I suppose, and the other major issue to do is that the reason why we were talking about, using this kind of alteration for body mass was because maybe a greater muscle mass and a greater, because people who are bigger need bigger hearts, bigger lungs, more mitochondria, bigger muscle mass, all of these reasons that happen when you scale something up. But these two people are the same height. So really, you can make an argument that they're probably the same stature in some way. This one just happens to have an extra 20 or 30 kilograms of body fat. So are they likely to have any less mitochondria than that person there? Or less muscle mass than that person there? Or a smaller heart? Probably not. They probably should be about the same. So maybe this is an indication of, okay, this person's big, and so we all got these slight prejudices thinking they're not very fit. Well, maybe this person's incredibly fit because their heart, lungs, respiratory system, whatever, muscular system, is twice as effective as this person's. They just happen to be carrying a bigger body mass. Okay, so something worth thinking about. And again, this is the nuance of the literature. There's so many ways you could take your assessment if you're going to choose this population. So there are different ways that you can scale to try and make account of these things. So scaling has been going on for over 100 years in different elements, and it was originally done trying to think about how you scale basal metabolic rate amongst animals, because you kind of think it's the same sort of thing. So in absolute values, an elephant has a much higher basal metabolic rate than a mouse, massively. But then if you scale for, say, body weight, then the mouse has a much higher relative oxygen consumption to body mass. So it kind of flips over. And then you can see all these different mammals that sort of fit onto this plot show a similar sort of pattern. So this kind of scaling of animals, or scaling to try and understand metabolic rate according to mass or size or something, sort of applies beyond the exercise physiology realm. So there are different ways of doing it. So we've got the relative to body mass, which I would say is probably the most common way people present VO2 peak data. We've got absolute values, which are the ones we've just talked about, so not taking into account anything other than whether you're able to deliver, utilise more or less oxygen than somebody else. Okay, so taking weight out of the equation, if you like. You can also do it relative to fat-free mass, so you can either measure or estimate fat-free mass and then make your oxygen consumption relative to that. And hopefully the reason why people would do that is to try and account for that scenario we just had. So if you've got two people who are the same height, but one's carrying an extra 20 kilograms of body fat, then you might make an argument that their stature is the same, and therefore you would expect them to have the same, if they're the same fitness, they should have the same maximum oxygen consumption if you took away that aspect of them having the 20 kilograms of fat mass. So you do that by just making it relative to fat-free mass. Okay, so you're trying to take away this idea that there's different ways of having higher mass. You can have a higher stature, you can be a bigger person, but by just carrying the weight, it's maybe not a good enough reason to consider someone to be less fit. And then finally, there's these funky ways called allometric scaling, which is basically just different ways of trying to scale according to either height or body weight. And I've put this up here because there's lots of literature on this to do with obesity, and it might be a really good way of some of you finding like a niche area to look at for your assessment. You might be able to really get on with this and think, actually, I'm going to apply this scaling for this particular reason. That might make a really good rationale for the study that you're going to do. And if you want a review article, there's one down here that sort of talks about a particular one that's quite common. Okay, so I'm not going to talk about that any further. Again, you might hate it and want to stay clear of it, but for some of you, you might see something within that thing. I think that'd be a really interesting thing that I can apply to the data we've got that might make an interesting question. Right, so let's get into the studies and see what they show. So, first study, kind of a weird one. So in this study here, they were basically trying to look at seeing whether people with obesity had a sort of comparatively poor VO2 peak and therefore cardiorespiratory fitness as people with heart failure. So they're trying to match them for lots of other things, but some have got obesity, some have got heart failure, some are healthy, or at least not necessarily healthy, but are in the hospital and have not got either of those two diseases. And they want to sort of see, what happens to their VO2 peak according to these things. So we've got patients who've got obese group, heart failure group, control. The interventionists that are interested in this obesity group of 43 people. We then had a control group of 222 people, a comparison group of 235 people with heart failure. An primary outcome variable was VO2 peak, and it was an observational study. So these are the characteristics just to show you sort of how they've matched them. So you can see that they're largely the same age. There's some slight differences in the significant, but generally they're sitting in their sort of mid to late 40s. There's slight differences in terms of whether they're women, white, African American, but if you're trying to think about trying to match these populations, it's incredibly difficult. But they've tried to sort of match them, at least in some respect, to being kind of relatively similar to one another. And now these are the results. So all we're interested in is the bottom line VO2 max. And so what we can see is in the obese group, their VO2 max relative to their body weight was 17.8. So 17.8 mils per kilogram per minute. The people with heart failure, their VO2 max was 16.5 mils per kilogram per minute, and then the controls were 21.3 mils per kilogram per minute. And then they did the statistical analysis, and basically what they found was that the heart failure and obese groups had a lower VO2 peak in comparison to controls, but there was no difference between obese and heart failure. Now if we look at the numbers, we can see there's a subtle difference between obese and heart failure, but there was no significant difference. And so they came to the conclusion that morbidly obese individuals have severely reduced cardiorespiratory fitness that is similar to those with established systolic dysfunction heart failure. So basically a type of heart failure. Okay, so morbidly obese, but no heart failure is the same as people with heart failure. Quite an important sort of like big thing to state really, because there's lots of people making an argument maybe that obesity isn't that detrimental to health in certain circumstances, and they're saying, well, actually it is. is as bad as heart failure, at least with regard to this outcome variable. We're going to revisit these numbers in a little while. But according to this, based on this scaling method, you know, being obese is very bad for you. Okay, so next study. So same kind of format, so case control kind of scenario. So 48 subjects, 18 males, 30 females, separated into 3 groups. 16 of them were obese, 16 of them were overweight, and then 16 of them were normal weight. The primary outcome variable is VO2 peak, and again it's an observational difference study. And they're looking at what you'd expect. They're looking to see whether VO2 peak changes if you're overweight or obese. Again, they've tried to sort of match and pick people that are similar, so they're quite comparable. So we can see the ages are fairly similar, so early 50s, early to mid 50s. They're a similar height. Mass obviously progressively increases, so in the lean people, mass is 67. In the overweight people, it's 76, and then in the obese, it's 91. So they're getting progressively heavier. Bear in mind, 91, even though these people are considered to be obese, that's on the low end of the spectrum, right? So in the labs that we were talking about, you know, this can be in the 100, 200, 150 quite commonly. I'm not sure what our population is that I've got for you, but I think the average sits in around about 120, something like that. So they're obese, but they're not really obese, right? And then there's some other measurements there about some of the other parts of their kind of fitness and activity and things like that. Right, so if we look at their values, well, if we start where the last study finished off, so looking at their oxygen consumption relative to body mass, that's the bottom one, we can see that the lean people, their VO2 peak is 30.5 mils per kilogram per minute. In the people that are overweight, it's 26.0. In the people that are obese, 21.6. So kind of what we'd expect. When we normalise relative to body mass, we definitely see this progressive decrease in cardiorespiratory fitness as people get more and more overweight. Okay, so that is unquestionable. That is what happens. If you take people, do their body mass relative to body weight, and people that are obese, you will get lower values relative to body mass. So that happens. Everybody's happy. It's just whether it's the best method is the question, right? So if we're looking at VO2 peak in those units, people with obesity have lower cardiorespiratory fitness. The question is whether it's the right way of doing it or not. So now this study also looked at it in absolute values, so the ones above. And what we can see in absolute values is that, so in litres per minute, the lean group have a VO2 peak of 2.12, the overweight have a VO2 peak of 2.03, and then the obese have a VO2 peak of 2 litres per minute. When they did the statistical analysis, there's no difference between these groups. But we can kind of see visually there seems to be some subtle decrease as people get heavier. But in terms of their analysis, what they say is, well, when we make it relative to, so when we do it in absolute values, that would be suggested that there's no difference in their cardiorespiratory fitness on the basis of their weight. Which is interesting, right? So it's like, well, which one do you pick? Which one's right? And again, I'm not saying I know the answer to this. I don't necessarily think I do. But it's interesting that there's no difference between those groups. And now if we go back to that previous study, they don't provide all the information to do this, so I had to make a couple of assumptions in values, but they never presented anywhere in that paper what the values were for these 3 groups in absolute values. So, but doing some kind of reasonable assumptions, you can kind of get to these numbers. So if you look at the obese group, and we set their height at about 1.6 metres, and their weight is 120 kilograms, and this is to get to the BMI that they presented. Their VO2 peak in litres per minute would be 2.1. If we know that the people are a sort of similar height, but then they have a change in their BMI, then we can presume that it's due to this decrease in weight. So if we can match the BMI, we make these assumptions about height and weight. So for the control groups, their VO2 peak would be 1.8 litres per minute. Now, allowing for the fact that I've made some assumptions because they didn't provide this information in the paper, what we can see is that the obese group, at the very least, kind of matches the control groups in terms of their VO2 peak. So this would be indicative and suggesting that actually, when we look at absolute values, there's no difference between VO2 peak or VO2 max between a control population and an obese population, that they're actually the same. And if you want to go away, because someone's done this, I took this from another paper, it was a comment, this is the original paper then there was a comment on that paper basically suggesting this in a different way, and you kind of follow that link if you want to go and find it. Alright, so then finally, well, what happens if we try and look at it in terms of lean body mass? How does that affect things? So, this is another paper, slightly different, but same kind of idea. Case control, 3 groups. We've got a control group, we've got a high body mass, but due to, so high body fat, HbF. So the second group is a higher weight due to higher body fat. Then they've got this third group, which is a bit funky. They've got a higher weight, but it's due to a higher lean body mass. So what we can see is if we look at body mass, we've got 73 kilograms, 80 and 83. But the reason these are heavy is because they've got a higher lean body mass in comparison to these two groups. Whereas this group's heavier because they've got a higher body fat in comparison to these two groups. So it's kind of heavy and fat, heavy and lean. I suppose the easiest way to think about it. So it's a weird study design, and also they're not obese; they're just overweight. So they have a higher body mass than the control group, but they're certainly not obese. Right. So so they're looking at a comparison to those things. It's the same thing. Main outcome variable being VO2 peak or aerobic performance. And this is what they found. So let's start off where we've done with the other 2 studies. So the middle one of those 3 that I highlighted is VO2 peak or VO2 max relative to body mass. And we kind of see what we'd expect. The lean group have the highest VO2 peak, 58. And that is higher than both the high body fat and the high lean body mass group, who are both about 50 to 53. So the leanest group has the highest value. If we now make it look at it in absolute values, well, we can see that VO2 max is kind of high in the lean group, drops down a little bit in the high body fat, and then high again in the lean body mass group. But I'm sure I got this right. But there was no significant difference between that. So again, I think visually we can see that there's a difference, but it wasn't significant, at least in this case. And then when we make it relative to lean body mass, so they sort of take measurements, work out lean body mass, so basically everything other than body fat. Well, we can see the numbers now increase, right, because we've taken away the body fat, normalised to body fat. So now it's 69, 65 and 63. So when we make it relative to lean body mass, the same sort of pattern I suppose, but actually the high fat group, that's slightly higher than the lean body fat group. Slightly, not significantly. But what we can see is, once we start using these other methods, we start to get to this idea, well, actually, maybe these people are just as fit as the leaner people. Probably can't run as fast, so in everyday life, you definitely still don't want to be the people that are overweight or obese, because you've still got to try and move that mass. But certainly in terms of their cardiorespiratory fitness, so like what's going on inside them, then they're probably as healthy as anybody else, possibly. So then, what kind of does this mean? So there's question mark over whether being obese influences your cardiorespiratory fitness. That's it. There's a question mark over it. It might well be that if someone here, ate for the next 2 or 3 weeks non-stop, put on 10 or 15 kilograms of fat mass and did an exercise test, that there'd be no difference in the result. Because body fat in itself may not have any effect on your function. But this is the important thing. If you are 15, 20, 30, 40 kilograms overweight for a long period of time, it has additional effects on your life, right? So maybe the question isn't, does obesity reduce cardiorespiratory fitness? Maybe the question is, do obese people have reduced cardiorespiratory fitness? Because obesity doesn't just come in isolation. It's not just about the fat mass itself. So people who are obese have lots of other things going on often. So there's an emotional element to it. So it might well be that more people, not everybody, but more people who are obese have things like insomnia, anxiety, lack of motivation, all of these kind of elements of like emotional elements that might stop somebody from doing exercise. By not doing exercise, it's going to have an impact on your fitness, irrespective of whether you're lean or not. And then there are also, possibly from our point of view more importantly, important physical changes that happen with you if you're obese. So people who have high body fat tend to have a higher blood pressure. There's a cardiovascular element to it if you're obese for a long period of time. People who are obese have a higher chance of getting coronary heart disease. People who are obese have a higher chance of getting type 2 diabetes, sleep apnea, all these other things as well. But certainly, it should be easier for us to think, well, coronary heart disease, if you're more likely to be a coronary heart disease than type 2 diabetes, then that might have effect on your VO2 peak, separate to the fact that you're obese in the first place. So it kind of comes back to the stuff that we talked about in some of the other sessions to do with, is it the primary condition, or is it the additional things associated with that condition that actually have the impact on your cardiorespiratory fitness? And there's loads of stuff you can research around this. There's so many questions you could focus on for your assessment if you wanted to. So I suppose this slide I'm just trying to say, well, maybe rather than just sort of skipping this middle bit and saying, well, people who have high fat mass are not very fit, maybe it's people who have high fat mass maybe have different emotional states which might make them less likely to be active and therefore impact their physical capacity, and also might have lots of physical stroke disease things going on which might therefore influence their physical capacity or VO2 peak. It might be this stuff rather than the fat stuff on the outside here that's of most importance. But there are arguments in both directions. Loads of stuff we've done. So how does this fit in with our sort of traditional theme of trying to think about this? Well, hopefully you kind of realise that if we can't decide whether obesity in itself has an impact on VO2 peak, maybe some of these questions become a little bit redundant. Because if we say they're the same, and that's the argument that we make in our paper, then maybe we don't really expect any differences in perfusion. Because the outcome's the same. They're both doing the same amount of activity. They're both able to do the same amount of exercise and have the same VO2 peak. So that's why I've not focused on this. But that said, it doesn't mean just because two people have the same level of fitness that they might not have alterations in the function of some of these systems. Right? So, and you could quite easily do a paper explaining that there's no difference, maybe in your opinion, between the two populations with regards to VO2 peak measured based on lean body mass or due to some allometric scaling or whatever it might be, but then really focus your attention on maybe ventilatory changes if you see something. Like you can do what you want. That's the kind of beauty of this piece of assessment. I've got no expectation of exactly what I want to see. I just want you to be able to make a clear rationale of an interesting study. So there's so many directions you could take it. So here's a bit of further reading just to help you on your way. So on the top left here, that's just a paper, kind of similar looking at the sort of stuff that we've talked about today. The top right one is that paper that's looking at scaling again. And so it's a review article which is going to put you into sort of like, give you lots of different other papers that you might want to look at if you're really interested in going down the scaling route. There's a paper there that's basically trying to make a case that body fat doesn't influence maximum aerobic capacity, so looking at it from that direction. And then the bottom three papers are ones that have looked at changes in exercise physiological variables in people with obesity. So you might go down this route if you really want to look at, say, look how it affects ventilation, or look how it affects perfusion, or something like that. So the first one is all about respiration in obesity and how that might change due to some of the stuff we talked about in the labs, like loading over the chest, things getting in the way of the diaphragm. So if you're interested in the respiratory side of it, you might be able to make a nice case for a study with regards to that. That's a good paper to check out first. Here's a paper looking at the VEV-CO2 slope, so the ventilator equivalent for CO2, which is one of the values that you get. This paper kind of makes a case in it's probably not different between people who are obese and people who aren't. But again, if you're interested in that, it might be a good paper to start looking at if you want to look at that as a variable of interest. And then finally, this one here is looking at cardiovascular function in obesity. So again, we've got these markers of cardiovascular function. We've got heart rate during exercise, this, that, and the other. So maybe that's something you might want to look at. And you could do any of these independent of the rest and still write a perfectly good assessment. You could get a first just looking at the cardiovascular aspect. You could get a first just looking at the ventilatory changes. You could get a first just really thinking about how scaling might alter someone's cardiorespiratory fitness, and maybe not even tackle this in any great detail. Maybe your paper would just focus around that. It's entirely up to you. As long as you've got a clear rationale and it makes sense, I'm happy with it. So take it whichever direction you want. Alright, so to sum up, scaling is important for interpretation. Obesity itself may not change VO2 peak to a great extent. Obesity is associated with these other diseases. It may be them that causes any reduction in VO2 peak if that occurs, and maybe it's these secondary problems to do with cardiac output and stuff like that, which is something you need to go away and read.